Greetings everyone. I am Uday Sharma from the Triple Department of Institute of Aeronautical Engineering. Today I am going to discuss about the topic the relationship between the real poles and real zeros in SISO sample data systems. Poles and zeros play an important role in the performance of linear time invariant control systems. Especially unstable poles and unstable zeros of control plans limit the performance. Examples: robustness, sensitivity, and command tracking properties. In feedback control systems, in, in most digital control systems, a sampler and a zero order hold allow decretization of a continuous time control plan. It is well known that the poles A are transformed as A positive or negative, where this the sampling period. T is sampling period, so that the stability is preserved. We, however, no such simple transformation for zeros. Only the limiting cases where the sampling period T goes to zero or infinity have been investigated by Astrom et al. For SISO systems and by Hayakawa et al. For MIMO systems. Hence, there is no information on zeros of the sample data systems and with a given sampling period t greater than 0. The main purpose of this note is to derive a relationship between real poles and zeros for SISO sample data systems, which is independent of the sampling period. Since the properties of the poles are well known, the relationship clarifies some properties of the zeros. In fact, using the parity condition, we can investigate if stability or instability of zeros is preserved under sampling. Here we can see the sample control plan diagram. We consider a discrete time composed system of a zero ordered hold, a plant, and a sampler in series as shown in above below, where g of s denotes the transfer function of a linear continuous time control plan. This configuration is used in almost all digital control systems, and the derived discrete time equation system is called the sample data system for g of s. This section derives the pulse transfer function of the system and states well-known properties. The control plan is an nth order, strictly proper linear continuous time system whose transfer function is given by g of s is equals to b of s by a of s, where a of s and b of s are coprime polynomials, and a of s is an nth degree manic polynomial. For simplicity, we suppose that all the poles of g of s are simple, but the discussion is valid even if g of s has multiple ordered poles. Throughout this note, we further assume that g of s has neither poles nor zeros at the origin, and it has an n plus p distinct real poles A, such that a of n is less than or equals to a of minus n plus 1, less than or equals to, and so on, a of minus 1 less than or equals to 0, a of 1, a of 2, and so on, a of p. And n complex phase C, f of 3d. More precisely, g of s is written as g of s is equals to b of s by a of s. That is equals to summation of I is equals to minus 1 to minus n. G of s plus summation of I is equals to 1 to p. G of s and plus summation of I is equals to 1 to nc. G of S. G of R comma is equals to B of I by S minus AI. G of C minus I of S is equals to P of I into S plus Q of I by S minus C I whole square plus D of I whole square, where A of I, B of I, C of I, D of I are real numbers that satisfy A of L. A of I is not equals to A of J. A of I is not equals to A of J. C of 1 comma D of I comma C of A is not equals to C of J comma D of J. And L not equals to J, D of J not equals to 0. Note that the pulse transfer function of the sample data system, which sampling period T or G of S is represented by H of Z is equals to 1 minus Z inverse into 1 by 2 pi J integral of 0 to minus J infinity to 0 plus J infinity. E of ST by Z minus E power ST into G of S by S ds, where U is a real number such that all the poles of G of S have real parts less than U. Since H of Z is a rational function of Z, H of Z can be expressed as H of Z is equals to beta of Z by alpha of Z, where A of Z is an nth degree monic polynomial and P of Z is a polynomial. We now calculate the pulse transfer function for G of S given by a simple real pole case. GR of S is equals to B by S minus C implies HR of Z is equals to beta by Z minus alpha, where alpha is equals to E power AT and beta is equals to B into E power AT minus 1 by alpha A. A complex pair case. G of S is equals to PS plus Q by S minus C whole square plus D square, which implies that C of Z is equals to eta of Z minus eta by Z minus 5 whole square plus psi square, where phi, psi, and eta are determined by phi is equals to ECT, e power CT cos dt, and psi is equals to e power CT sin dt, is equals to minus QD psi of minus QD 5 minus 1 plus P into C square plus D square plus QC psi by D into C square plus D square, where eta is equals to minus QD into 5 minus E power 2 CT minus P into C square plus D square plus QC psi by D into C square plus C square. Summarizing the above results, the transfer function of a sample data system for G of S given by equation can be expressed as H of Z is equals to beta Z by alpha Z is equals to summation of I is equals to minus 1 to minus n HR comma IZ plus summation of I is equals to 1 to P HR comma IZ plus summation of H I is equals to 1 to NC HC comma IZ, where H R comma IZ is equals to beta I by Z minus alpha I, and H of C comma IZ is equals to mu I C Z by mu I Z by C eta I by Z minus 5 whole square plus psi square, where alpha I comma beta I and psi I, phi I, and eta I are defined by above equations with indexes I respectively. To avoid confusing caused by pole zero cancellations, we consider a class of sampling periods denoted by tau. Tau is equals to t greater than 0, where n is equals to 0. Tau is equals to t greater than 0 for d of I not equals to 2k, t and phi by t. And d of I plus or minus d of j is not equals to 2k phi by t, where I naught is equals to j. I comma j can be equals to 1 minus 1 difference of nc. K is equals to plus or minus 1, 2, and so on, where nc is not equal to 0. We know that t belongs to tau is not restrictive. Since a property which holds for any t belongs to tau is satisfied for almost all positive sampling periods t. Preservation of stable or unstable zeros. If the controllable plant has a minimum phase property, that is, all the zeros are stable, then many design algorithms for modeling matching or adaptive control schemes can be applied. This selection derives the sufficient conditions for the stable or unstable zeros to be preserved under sampling using previous results. We first discussed the preservation of the numbers of zeros between any two poles. Note that theorem 1 does not necessarily imply that the number of zeros between any two poles remain unchanged as shown in the above. However, there is a case where the number of zeros between any two poles is preserved, as stated in the following lemma. Suppose that the number of sign changes in the sequence b a minus n and so on to b of ap is n minus 2 or n minus 1, then g of s has only one real zero in every interval a of j, a of j plus 1. For j such that sign b of aj is not equal to sign b of aj plus 1. In that case, h of z has only one real zero. In every interval alpha j, alpha j plus 1 for any sampling period, t belongs to tau. When the continuous time system g of s has a multiple ordered poles, it is enough to rearrange the proof of theorem 1 as follows. We mention only the case where all the poles are real. Since a similar discussion can be carried out even if g of s has multiple ordered complex pole pairs, we assume that g of s is expressed as g of s is equals to summation of I belongs to n to summation of j equals to 1 to mi bij by s minus aij. Since the sample data for bij by s minus ij whole power j is represented by bij by z minus alpha I whole power j plus and so on bi, 1 z minus alpha I, where bij is equals to beta ij is equals to bij into e power ait minus 1 and t into e power alpha it minus the whole to the power of m minus 1 by ai. Here, we have developed a relationship between real poles and real zeros in sample data systems, which is independent of sampling period. The relationship with the preservation for the parties of real zeros, between any two real poles enable us to investigate the preservation of stable or real unstable zeros, the sufficient condition for the preservation under sampling. Thank you. This is Uday Sharma signing off.